Okay, so I'm Andy Rudoff. I work at Intel. The other presenter is Steve Byan, who works at Oracle. And we thought it'd be handy to do a talk all about flushing with persistent memory, because the questions come up about flushing all the time, and why do I have to worry about it, and what am I supposed to do, or can it just be done automatically by hardware, you idiots, and stuff like that. So this is kind of a overview of the flushing part, but it does presume that you know a little bit about persistent memory, at least what it is. And you know, so every time I don't have a section that introduces what persistent memory is, but I can just say it in a couple sentences. We're talking about byte addressable persistence, something like an NVDIMM, something where you can do loads and stores to it, but it maintains its contents across power failures. But just because something maintains its contents across power failures doesn't mean that all your data structures are consistent unless you plan them to be. So that's why we're talking about this. So by the end of this talk, hopefully, if I do this right, you'll understand why we talk about flushing so much, why it matters for persistent memory, and when do you have to worry about it, and when don't you have to worry about it. And then in particular, I want to cover the difference between visibility and persistence. This is a very, very key aspect of persistent memory. We're going to talk about these interfaces, like the Linux interfaces, the standard POSIX way of flushing, and the Win32 API standard. These are like 30-year-old interfaces that have been around a long time. Do they work with persistent memory? I'll talk about that. In the SNIA NVM Programming Technical Workgroup, the TWIG, we coined the phrase optimized flush for a flush that is maybe more optimal than these standard interfaces, and we're going to talk about what that is and when it's safe to use them. And then I'll talk about, I am the Intel guy, so I'll talk about the Intel instructions for flushing, this thing that puzzles a lot of people called deep flush. And then finally, we're going to touch on flushing to remote persistence, but actually later in this same room here, I think, on this track, there are sessions on RDMA and persistent memory where you get a lot more detail. So that shows you why we're doing this. So why do we even talk about flushing? I'm a programmer. I'm an application programmer. Why do I even care about it? You know, isn't it kind of a weird thing? I don't remember in school the teacher telling me flush after you do stores to variables and things like this. So why are we suddenly talking about it? And actually, it's not really, flushing isn't really the right term. It's really about store barriers, right? It's really about knowing that something is persistent before something else is persistent. And I just kind of drew up a quick representative example here. So this is not to say all programs work this way, but the idea here is that, you know, I've got some program and I'm making changes to persistence here, and I want them to be transactional, right? I want them to kind of hold together. So one way of doing that is maybe to write the information to a log, and then when you know it's persistent, then you write another little record there, kind of a sentinel value that says, okay, this is now a valid record. And the point is that if you crash on recovery, you come back and you look at these things, and very often a program will say, oh, okay, this one's valid, transaction B here is valid, so I can infer that transaction A is valid, right? Because they're ordered. That's what store barriers are all about. And programs do this all over the place without even realizing it. So this one's very explicit. This is designed to work this way in my example, obviously. But the number of places in code where there's these assumptions that you see something that's valid and you want to infer that all these things that happened before it are valid, it's all over the code. It's all over file system code. It's all over database code and other applications. So why do flushes matter? Well, I'm saying because they are store barriers, right? You often have to have these sort of store barriers. So that's the basics of why do we even care about this. Now let's talk about how the hardware works. And again, I'm the Intel guy, so I'm going to talk about how the Intel hardware works, but other platforms will work similarly. So I show here on this this kind of diagram, this chart here, down at the bottom is a non-volatile DIMM, this little square guy here. And the store instruction on Intel is called move, and you can see it kind of makes its path through these red arrows heading for the persistence here. And you know, you might say, well, why can't we just, as a programmer, assume that when the move is done, it's persistent, right? And the answer is, technically you could build a box like that, but these caches are huge in modern hardware. These things are many, many megabytes in size. It takes a long time to flush them. So if you wanted to make things persistent, you'd either have to have some sort of a UPS or big batteries or something to flush these caches on power failure, or you'd have to have the caches be write through, and that would slow everything down. So really it's kind of a matter of practicality. Will there be machines where you can assume something's persistent right after you do the move? Absolutely. Absolutely, there will be machines. I know companies that are building them, but they probably, they won't be every machine, right? And so for that reason, there's an ACPI property that you can look at runtime to decide whether flushing for the caches is necessary, whether it's done for you automatically, essentially. That's in the current ACPI spec. So we're already planning for it, but you can't just ignore the fact that you have to do flushes, because they're definitely, it's not going to just go away. I have drawn two of these red boxes here. One, like I say, for a custom platform, you can assume things are persistent once they enter that red box, but that's not the common case. The common case is this minimum required here. So we require this of all of our machines that support persistent memory. This is a hard requirement. And this is already true with the NVDIMMs that are shipping today. If you go today and buy an NVDIMM from one of the companies that's already selling them, they will require that you have this feature called ADR. ADR stands for Asynchronous DRAM Refresh. And what it is it's a feature that says any stores that haven't quite made it to the DIMM yet, they're still in the memory controller, are automatically sent to the DIMM on power failure by some stored up energy that the system is required to keep. So this is a minimum required protection domain. Every platform will have it. This is the wish list. Not very many platforms will have it, but hopefully more over time. And so at runtime, the hardware has to give you some way of getting the store from here down into this minimum required thing, and that's what these flushing instructions are about. And I've listed all the flushing instructions here, but actually the one you care about is the top one. It's called cache line write back, CLWB. For virtually every use case I can think of, you're just going to use the CLWB. The software is just going to use the CLWB instruction. There are some kind of fringe cases where you use some of these other things, but I won't talk about that here. You can see them in our libraries and so on if you want to see. The point of this is that this is how the hardware works. So I just want to be really clear about this. I'm not telling you to just start sprinkling CLWBs through your code. This is how the hardware works. Where it gets interesting is how the software works. Okay, so let's move on to that. So this diagram here, notice it doesn't say Linux or Windows on here, because this is kind of an abstract idea. Now this is the diagram, we drew this in the NVM programming twig a couple years ago, 3 years, I forget how long the twig's been running now, 4 years ago? No, has it been that long? It's been a long time. So we drew this thing, I basically drew it on a napkin in a hotel, and then it became the spec. And the rest is history, right? And so really everything that's on here is true. It's all been delivered in Windows and Linux. The implementation details are a little different, right? So where I just wrote NVDIMM driver, this is some collection of modules and kernel code in both of those OSs, and the actual collection doesn't matter for this conversation. But the point is that you have this non-volatile DIMM down at the bottom here, and there is some set of drivers that manage it for you. And there's a persistent memory-aware file system that you build on top of this persistent memory. You use standard file APIs, like open, close, read, write on Linux, to open these files. And once you have one open and you mmap it, you get this arrow on the right where you have direct access. And as it turns out, both Windows and Linux call this feature DAX for direct access. So it's handy, they both ended up using the same term. And once you have this direct access, you are doing, literally you're loading from the media without taking page faults or paging at all or copying things into DRAM. There's no in the steady state here after you've done some protection faults and things like that. There's no kernel code that runs, there's no interrupts, there's no context switches. So it's very direct, it's cool. But the question is, now, how do you flush? How do you make sure that something's persistent? Well, there are already APIs, the standards for doing that, okay? And they work. So let's talk about that. So is flushing something that's new for persistent memory? No, those same APIs for memory mapping files, they've been around for 30 years, and it has always worked this way. After you do the stores, you have to use the API to flush. That means calling msync or fsync or FlushFileBuffers, depending on the OS. So this is not a new requirement for persistent memory. It's always worked this way. And here's the really important point here, that these stores are visible before they're persistent. Again, 30 years of this. This is not a new thing, because we certainly had people report this as my gosh, this persistent memory thing is a horrible bug. I do a store and everybody else sees it before it's persistent. And I'm like, well, yeah, but that's how mmapped files work. They have always worked that way. So we didn't change that, and that's still how they work. But you have to, as a programmer, you have to be cognizant of that. Do the standard APIs work for persistent memory? Absolutely. So if you just follow the standard, just like you always have for memory mapped files, and you call msync, it will do what you think. It will make the persistent. Now, of course, what's happening down in the kernel is saying, oh, this is really persistent memory. So instead of pushing a page down through the storage subsystem, I can use this CLWB instruction. So the kernel is using the CLWB instruction for you. Okay? Well, if the kernel can do it, why can't the application just do it? And the answer is, you can, as long as you have conditions met that say it's safe, right? So why do I have to give you this caveat? Well, the file system is in charge of where things are laid out on the media. The file system can decide to move those things around. It can decide when other metadata gets updated and so on. So POSIX says that the file system gets to do that when you call msync. There's nothing in POSIX that says, oh, and by the way, if the application flushes it directly, it has to be guaranteed to be persistent, right? So because of this kind of wording of POSIX, file system developers know that they can postpone things until an msync call, right? And so in order for this to be safe, the file system has to know that you plan to do flushes yourself from user space. Okay? So on Windows, the NTFS DAX changes completely support this. It is safe on Windows to do these CLWBs from user space. No problem. On Linux, the ext4 and XFS file system maintainers have shown some trepidation about making this be safe, and I'm going to show you where that stands on a slide that's coming up, but we're actually making some pretty good progress on that. But instead of you looking to see which file system it is and whether it's safe or not, you could just use a library to determine when it's safe, and we've written libraries to do that, and I'll explain how that works too. Okay, so now let's define what these different types of flushes are that you care about as an application programmer. The standard flush, like I said, these are the standards that have been around for 30 years. They work. Honestly, if you're going to do changes, where you flush every few minutes or when the program closes, just stick to the standard, right? It'll work. It's made for big bulk flushes, and there's really, it's very simple, it's well understood. If on the other hand you're going to do 1,000 flushes a second because you're doing all these little tiny transactions, you might not want to drop into the kernel for each one of those, especially because these interfaces all take locks and things like that serialize things. So in that case, you might want to use optimized flush. Optimized flush is again, it's the SNIA twig term for doing these flushes yourself directly from user space. It's optionally supported, like I said, but we're getting it supported more and more places. Certainly supported by the hardware, but we're getting the support into the OS. And this avoids you doing things like grabbing those kernel locks I mentioned. msync also requires that everything get rounded up to page sizes. So even if you're trying to flush one cache line, you end up rounding it up. And the kernel path actually that msync takes can be pretty amazingly long. So optimized flush can be quite a performance boost. Okay, so now there's this other thing that we put into the most recent spec, the SNIA programming model spec, called deep flush. So deep flush is all about what happens in the face of hardware failure, okay? Because, you know, like I told you before on this, I'm just going to go back up to this picture really quickly. Once you get something into this red box down here, now it's ADR's job to make sure that things are flushed on power failure, right? So you might not be the stores might not be in the media at all. So what happens if ADR fails? What happens if you have some sort of, now this is a fault, it's a hardware fault, but in most cases you're just going to say, oh, sorry, hardware fault, I guess I have to repair the hardware. But there are some things where we want to make sure that they're all the way down onto the DIMM whenever possible. And I'll give you an example of that is things like the journal for ext4. Right, when we write to those journals, it's handy for us to just flush this stuff down here. And so we have a kernel-only way of doing that flush. It's called a write pending queue flush, or a WPQ flush. And in the spec, we ended up calling it a deep flush because it flushes, you know, deeply in a manner which is deep. So basically, what you're doing with deep flush is you're deciding to give up some of your performance for maybe higher reliability. Okay, it's not something that I would recommend that you use unless you have a very specific case for it. But I wanted to explain what it was. We mostly mean it for file systems to use for their journals. And then finally, remote flush. So what if you're doing RDMA to persistent memory? Persistent memory is memory. It can be a DMA target, so it can be an RDMA target. But again, once you've RDMA'd something to a remote node, how do you know that it's all the way to the persistence? How do you know it's not sitting in some cache in the NIC or something like that? So there's a talk this afternoon about RDMA in this room, so go to that to get some details. And also, Steve's going to talk a little bit more about RDMA in a minute. Yeah. The difference in performance between a regular flush and a deep flush is highly dependent on how much the deep flush ends up waiting for. So it's called a deep flush, but actually on the Intel hardware, what it's really doing is it's marking everything and then waiting for it to drain. Because it's not a cache down in the memory controller, it's a queue. So there's no flush operation really. And so it really depends on how full that queue is. But it can be, depending on the architecture, it can be several times what a normal flush. It can be pretty significant. And also remember, it has to go to every memory controller. So it can be a pretty big difference. That's why I say avoid the deep flush unless you absolutely know that you need to do it. Okay, so the state of the ecosystem today with respect to everything I've been talking about, we have everything that I've talked about has been described in ACPI 6.0 plus. The way that NVDIMMs are detected, whether they have these different types of flushes, the flush hints and things like that, all that stuff is encoded into the spec in ACPI and it's public. You can read about it. The OS exposes persistent memory to apps using that programming model in DAX that I talked about, and that's fully supported. So Linux has 2 file systems that support DAX right now, 2 upstream file systems. There's also the Nova file system, which is not upstream yet, but also not only does it fully support DAX, but it supports user space flushing, and it even supports replication of DAX files. It's the only file system that does that. I'm just giving you a plug for this cool file system that I'm hoping to get upstream at some point. But anyway, so that's in Linux. Windows NTFS is the file system that supports DAX right now. And both of them support optimized flush to some level. Like I said, Windows, it's safe on NTFS. On Linux, it's currently considered unsafe. However, we do have this way of going around the file system and using the device directly. It's called device DAX, in which case you are allowed to do user space flushing. So you can do that today. That's all upstream. Just one second. And coming soon in this kernel, upcoming kernel, I think it's going to be in 4.15, we've gotten some new flags added to mmap that say, all right, file system, I need you to agree that it's okay for me to do this user space flushing. So we actually finally have a solution. It's just not quite upstream yet, so I didn't want to describe it in great detail. So yeah, was there a question? So device stacks it's a way of using the NVDIM without a file system. So you actually just use the /dev/ and there's a like DAX0. You use the ndctl command to put it in that mode. And then at that point, there is no file system, so there's no file system to gripe at you for doing user space flushing. In fact, user space flushing is the only thing that works with device stacks. msync doesn't work.
DAX is not a block device though, right? It's a character device.
Right. And it's not a, you don't want to take a device stacks device and mount a file system on it. In fact, you can't. And in a way, it was a Band-Aid because we were still trying to negotiate these changes that we think are coming. So device stacks, I expect it to get a lot less interesting as soon as we get these changes in 4.15. Yeah?
What's missing from making it safe in Linux is the msync or mapdirect?
Exactly. The mmap flags, the new mmap flags, msync and mapdirect. That's right. There are patches out already, under discussion right now. Well, I mean, they're flags to the mmap. So you were already calling mmap to get your thing. So you just have to add a flag. But if you, are really thinking this through, you'll use libpmem, and libpmem will just handle it for you. Because libpmem will just add the flags. If it'll in fact check to see if the flags are there, are supported, and if they're not supported, it'll just fall back to using msync. Uh-huh. Right. Yes. So it's a good point that the mmap already has all sorts of stuff that's going on with it inside of glibc, and this will probably have to affect that code as well. But again, we'll hide it in a nice library for you, and you can the libpmem code is designed to help isolate you from that, but also to give you code that you can just steal. If you want to know how it works, there's nothing that says you have to link with the library. You just steal the code out of the library. Okay, so remote flush is something that currently requires an extra round trip to send to the remote node to say something, to do some sort of flush. And we're working to get rid of that extra round trip by making changes to the RDMA protocol, to the NICs, to the cores, to the libraries. So it's a big heavy lift. It's going to take us a while. But again, this afternoon you can hear more about that later this afternoon. Deep flush is already, I think that's already out now in the latest SNIA twig spec. And then doing more complicated things, building on top of this, like doing transactions and allocating, that's all stuff that's a huge work in progress, right? There are a lot of people working on this. There are a lot of different libraries. We at Intel have started out with the libraries that we put on pmem.io, but I think there's always more and a lot more language support that's coming. The virtualization of all of these things is happening in pretty much every VMM that I can think of. And those companies that own the VMMs will have to announce it themselves. I can't announce it for them. But I can tell you KVM changes are already upstream, and actually I think the Zen changes went out recently upstream. So those things also support everything that I'm saying here. So can visibility equal persistence? Why can't we just make them the same? Well, you can, like I said, and I'll just kind of cover this quickly again, but you would need to battery protect these caches or make them write through. Making them write through would just kill performance. And battery protecting them is expensive. So don't expect that to happen soon. But if you do this to your own machine, if you decide, I'm making a product and I control my platform, a lot of appliance vendors are going this direction, do things just work. This is the trap that I just want to warn people about. Do you then just treat persistent memory like memory? Oh, things just work. Like now the compare exchange instruction, does it just work now? Because there is no instruction that says compare exchange and flush to persistence. But if the flush to persistence is done by these battery backup systems, does compare exchange work? Mostly. Maybe not entirely, but you do get compare and exchange back. What about transactional instructions? No, they're still not transactional, right? Because remember that a TSX instruction can fail in a way that requires you to go back and take a normal lock. And if you go back and take a normal lock and then you crash, you now are holding a normal lock in your persistent memory that you haven't resolved. So, this is the kind of stuff I highly recommend that you leave to libraries. We've thought it all through. But the real issue here is that algorithms are full of these assumptions about volatile memory all over the place, right? Most programs assume that there's a lot of stuff it doesn't have to worry about because when the program dies, all the memory goes away and the contents don't matter anymore. So bottom line, some custom platforms will have that flush on fail. Maybe someday all the platforms will, but it's not going away. The need to flush is not going away anytime soon. So you should look at that ACPI property or use a library that looks at that ACPI property and just honor what it says. Again, for deep flush, I really did intend it for file system journals, so ext4 and TFS. You can, if you decide that your application has to do it, you can do a deep flush, and the way that works is that, at least currently on Linux and Windows, it actually is plugged into these calls. So if you do call msync or flush view a file, you will actually trigger a deep flush. So we didn't make a separate API for it because we figure you're already doing that trip into the kernel, you're already taking those locks, things like that. The actual deep flush thing, although it is higher overhead than a normal flush, than an optimized flush, it's still a pretty small part of the trip through the kernel. So you can just do a deep flush just by calling msync. And that's why I say this should be your going in position. If msync is fast enough, then you're great. Why bother using all sorts of other types of things? When not to use deep flush, well, if it's performance critical, deep flush really isn't for you. Optimized flush will work fine as long as there's no hardware failure, and if there's hardware failures, you probably have other kinds of recovery you have to do anyway. So my advice is, don't micromanage flush versus deep flush thing. It's a premature optimization until you are kind of proven that you have to. Okay, so the libraries, like I said, they're on pmem.io. The libpmem is this library that provides things like, is it safe for me to use user space flush? Which instruction should I use? It has an API that figures it out for you and so on. But actually, most people use these transactional libraries here instead of libpmem. These libraries use libpmem. But once you use the transactional libraries, then you kind of stop worrying about the flushing. So if you must do your own flushes, I suggest that you go look at libpmem, either use it or steal from it so that you don't have to reinvent the wheel. But consider using a library that just does the flushes for you. So just to give you an example, this is a C++ example. There's kind of too much to go through here, but this is a push operation on a queue. This little syntax here in C++ is called a lambda. And basically everything between that open red curly brace and the closed red curly brace is transactional automatically by our library. And so this is a memory allocation here. Here's a bunch of pointers getting changed and all this. And in the face of crash or machine crash or program crash, either all of this happens or none of it happens, right? But where are the flushes? Right, there's no flushes because the library is doing it for you. And so all this stuff that I just told you, you can just now forget it all. You can say, well, why did I sit in this class? Because I had all these, I had to understand what the heck a deep flush was, but now I don't care, right? The library just took care of it. And it's the same for Java. We have a Java library out there. We have something called a persistent sorted map. It's just like the normal Java sorted map. It has the same operations, like a put on it. Again, where are the flushes, right? This is all transactional, but it's done in the library, right? And so I don't care what library you use, but I highly recommend you use libraries, right? Use these things that have been debugged and tested and performance tweaked and all that kind of stuff. So the other kind of cool thing about these libraries is that without changing what API you're using, they can be configured to do replication, right? So they can do this RDMA thing. And we call that persistent memory over fabrics, and there's a whole talk on that coming up at 4 o'clock in this room. So I just am sort of whetting your appetite here that there's a built-in RDMA in these libraries as well. Okay, so at this point, I'm going to switch speakers over to Steve. Here, why don't I just hand you this? You can click it. Here's the thing.
Well, thank you, Andy. All right, so we talked a bit about remote flushing here. So the question is why it's any different than a local flush, right? So locally, a local flush is fast. It's just a couple of CPU instructions, essentially. So that, there's no context switch involved. There's no pointing context switching. It's and it's offers the opportunity in a superscalar pipeline to be overlapped with other instruction execution. So perhaps even some of the latency can be hidden. So locally, it's quite fast. But the point of flushing remotely is to go to over a network to another failure domain, and this is mediated by software, not by hardware instructions. So there's the CPU superscalar pipelining. Doesn't offer you any parallelism. Right? So what we'd like to do with this is a preview of what might be talked about in future talks on RDMA. What we'd like to do is to push some of that synchronization into the protocol and into the networking hardware. And I'll maybe explain that a little more clearly in a few slides or so when we talk about this new feature that we're trying to specify in the SNIA NVM programming twig called asynchronous flush. So let me introduce what asynchronous flush is by first talking about optimized flush in more detail. So optimized flush is part of our current programming model. The stack on the left is instruction ordering, instruction flow in a thread. And the stuff on the right is kind of the persistent memory operations that are happening in hardware. So a normal application might, using the optimized flush programming model, might do some computes, and then do a store to persistent memory, do some more computation, do another store to persistent memory, some more computation, another store, and now the application needs to close that persistence epoch and make what it's written to persistent memory in the cache now become durable in persistent memory. So it's going to invoke this optimized flush operation. And that optimized flush operation basically writes back the cache lines that contain those stores. And then a fence operation that ensures that stores by that thread subsequent to the optimized flush are not visible until the data that has been stored previously and flushed has become durable. So this prevents side effects from becoming visible until you're sure that your data is persistent. So you can see that's kind of a lengthy operation that you perform a bunch of computation and get things sort of staged in memory. And then it's somewhat analogous to a write call. You say, okay, take the stuff that's in memory and now make it durable. So asynchronous flush tries to essentially pull a model that's similar to async I/O, where to get back some of that pipelining capability, to let you overlap the write back of the data with further computation. And it does that by splitting this optimized flush into two pieces that we call async flush and persist barrier. So in this model, you would do some computation, do a store to persistent memory, a cache line of persistent memory, and then invoke an asynchronous flush of that cache line. And that allows the hardware to start asynchronously flushing that data back to persistence domain. while your program can continue computation. Then when you get to the point where you need to close the persistence epoch, you invoke a persist barrier. And the persist barrier, again, ensures that subsequent side effects stores don't become visible until this fence completes that when all of the previously asynchronously flushed data becomes storable. So this lets you get some overlap. And hopefully you can find enough useful computation to do to hide the latency of the flushes. This becomes even more important when we look at remote situations where you're flushing remotely over RDMA. So in this case, the column on the right is the RDMA operations rather than local CPU hardware. So similarly here, as in the local case, asynchronous flush would invoke not a cache line write back, but an RDMA write. So write the data that you've staged and written with your store to carry that over to the remote node. And of course, that's much more expensive than the local cache line write back in terms of execution time. So again, we stack up multiple of these, fire them off with asynchronous flushes. And then when we get to the end of our persistence epoch, we invoke a persist barrier, and that's going to have to invoke a remote RDMA flush, which is going to have similar semantics to the local fence. It's not going to complete and allow your program to proceed until all the previous writes have reached the persistence domain. Of course, that's much longer, and one of the issues that we talked about in terms of trying to improve the RDMA protocol for this is to allow you to, in some circumstances, you need to just ensure ordering of persistence. You don't actually need to stall the current program execution until stuff is hit the persistence domain. You just need to make sure that subsequent stores to persistence don't happen until previous ones have. So for example, you might write multiple records to a log and only need to know that those records retire in order. And at the point when you want to commit the entire transaction, then you need to wait until everything's in the persistence domain. So those intermediate writes, you don't need to necessarily stall the program execution for the entire time. So if we could find a way to pipeline subsequent computation and asynchronous flushes after this RDMA flush, then we could regain some additional parallelism and hide more of the latency. So hopefully Tom will talk about that more in his RDMA talk later. So as I said, this is a work in progress in SNIA and the NVM programming twig. And really this stuff's already available in the instruction set architecture, and it's really implemented in libpmem. But the issues that we're trying to deal with in the twig are to specify the semantics more precisely in a generic way that aren't specific to a particular instruction set architecture, and perhaps in a more less restrictive way that's specifies the least amount that we need to specify to make them useful. So we need to specify the semantics of this asynchronous flush and this persist barrier operation. And our goal in doing that is to ensure that the semantics of them are compatible for both the local and the remote cases. We don't want you to have to use a different programming model depending whether you're replicating or not. So examples of what we mean when we're talking about the semantics are questions like, for asynchronous flush, what stores have to be flushed? So this has a number of aspects, right? The compiler optimizer can reorder instructions. It would be bad if the optimizer scheduled your store operation to happen after your flush, right? Kind of defeat the purpose. So we have to have compiler reordering barriers. Similarly, for the superscalar CPU pipeline, it does instruction reordering. We similarly have to have pipeline barriers to ensure that the stores don't get pushed past the flush. And then there's this question of, if another thread does a store that they later flush and want to be persistent, which stores are visible to what thread, right? To define the ordering between stores between multiple threads. Probably just defaults to the programming language memory model. Stores that happen before you issue the flush are the ones that are going to happen, but we need to define that. Similarly, for the persist barrier, we have the same questions about compiler and CPU instruction reordering. And one thing to note is that this persist barrier is thread local. Doesn't apply to flushes done by different threads. So that's a concern that we need to be careful about. In our previous model for optimized flush, a lot of these semantics weren't really visible to the programmer. But now we tear that apart into separate operations. We have to define what the internals look like. All right, so to summarize, there's a number of flushes that are available and a few more that are going to become available. Some of them are basically implemented in hardware. Some of them are implemented in software. Flushing won't go away anytime soon, and probably never if you need to do replication to another failure domain. When you're programming, you basically want to use the standard or optimized flushes and not worry about the special cases for 99% of the time. And strongly urge you to use libraries or language level support, to hide the complexity of this stuff, because it's not just flushes, it's also ordering the stores in a way that then becomes recoverable. So you really, for practical purposes, want to use a transaction system that someone else has validated for you, either in a library or a language runtime. But if you're writing one of those libraries, then you need to worry about this. So we're still working on some of the details, but most of the cases are defined in the 1.2 spec that's available now, and they're implemented on Windows and Linux, so you're free to start. All right.
So we
Thank
have
you.
time for questions. We have about 5 minutes left, I think. So I'll stand up here. We can, either one of us, if you have any questions. Like, what is flushing again? Go ahead.
Sanity checks, nothing for BSD. Any
So I'm not aware of any work on BSD to support the DAX idea yet. However, I am aware that people have sent us patches or are preparing to send us patches to the library, NVML for BSD, to get it to build. So that must mean somebody's working on DAX somewhere, but I don't know who it is or any details on that yet, but somebody is. Hope to see it. Yeah.
Well, it requires hardware support. It's already in the Intel ISA. So, previous to the most recent enhancements to the Intel instruction set, there was a synchronous CL flush instruction that coupled the persist barrier with the flushing operation so that they were unitary. The extensions to the Intel ISA separate those into a CL flush opt or a CLWB, followed by an SFENS, which implements the persist barrier. So it's basically already there in the ISA. As I said, the question that we really need to resolve is how to define that in a more generic way for other instruction sets.
Steven.
I gotta ask. So NVMe is standardized persistent memory units. Anyone looking at tying that into the library?
The controller side, NVMe.
Basically persistent PCIe bar.
Yeah. So, but still, it's through a PCIe bar, right? It's not cache coherent.
It's certainly not cache coherent. It
So,
doesn't even have struct page mapping.
right.
Upstream version.
So, I think a lot of people, I think to answer your question, a lot of people are looking at how to use it, but I don't think that we're just trying to combine those two ideas into one because of the lack of cache coherency. It's a kind of a different animal. Whether we would expose that to user space, I don't know. It's a good question, but I think we're only limited by our imagination there. We have to figure out what's the right thing to do with it.
I think it's tied into RDMA. It's interesting because then
Yeah.
RDMA one PCIe device to another that has a persistent memory DMA target.
Is there somebody in the room who has some experience with that? Oh, it's the guy asking the question. Good work. There was another one? Yeah, go ahead.
Well, the left side is the instruction ordering, right? So, this is the program sequence that you need to write. You need to write a program sequence that invokes this asynchronous flush operation or the optimized flush operation. And then the stuff on the right is basically, what those instructions make happen in the hardware.
Okay. Right. It's specific hardware is specifically getting this data and
Yeah, but the software, there has to be some way for the software to express the store barrier, right? And so, the who ultimately is the software has to call the API or use the language feature or however it happens to be expressed. So for example, for our libraries, the NVML libraries, it's an API or it's the closed curly, like I showed in that one transaction is essentially where it happens. But, like Steve said, then it's kind of up to the hardware to honor the semantics of what a fence does and make sure that you've waited for all the previous things to become persistent. So the who is maybe everybody. I don't know. So the question is, do they have to run on the same core? It's actually the fence is for a per hardware thread. Yes. So in other words, if I do a fence on one hardware thread, it's not going to wait for a store from another hardware thread.
Yeah, the interesting question is what that flush is required to flush with respect to stores done by other threads.
Yeah. It actually allows all sorts of nice pipelining tricks that the CPU does to make it a little more optimal. Yeah, go ahead.
so what is the mechanism on a normal shutdown when it's out of power failure, keeping everything persistent?
So on a normal shutdown, what's the mechanism for making things persistent? And yes, so ADR still is triggered on a normal shutdown to make sure everything's flushed out. But also the operating systems also tend to use that little WPQ flush thing that I said is an kernel thing just to make sure that it goes out because the ADR's OS can't trigger an ADR. It has to be done by the BIOS, and the OS doesn't trust the BIOS guys. The BIOS guys don't trust the OS guys, so they both do it.
But for NVDIM-N, getting it out to the NVDIM isn't enough. You have to tell it to write its command, right?
Yes, and the ADR triggers that on an NVDIM-N, the copy to the NAND, and so does a power loss, which is essentially the same ADR. Power loss triggers the ADR, which triggers the NVDIM. So yeah, so on a normal shutdown, I think it still uses the same ADR logic. Honestly, I'm not an NVDIM-N expert, but I can tell you what the 3D crosspoint DIM will do. That doesn't help you. Yeah.
What happens is, as well as ADR, there is a loss of power detected by the FPGA. It is still up to the peasant superpath or whatever, and it does the jump from the DRAM into the NAND.
Yeah.
Is that standardized or specified?
Well, there is a spec for ADR.
Or when it triggers also, or just how it works when it doesn't?
That's a hard question. I don't know the answer to that one. I'll have to go digging for that.
SNIA and JEDEC have standardized around NVDIM-N, so
Right.
Yeah.
That's
Yeah, he's really talking about a platform question. So yeah, you might want to reach out to me by email, and I can dig up the answer on that one. I just don't know it off the top of my head. So it was a good question.
One additional thorn in that one is, does the PCI switch still maintain power as the system's going down for those devices on slightly different buses, the DDR and PCI storage?
Right. Yeah.
Connected.
Right. So part of the ADR spec is what the power supply's responsibilities are, and it's not just about maintaining power for a certain hold-up time, but also giving a signal that the power is going to go away. And we are out of time. So any more questions, you can catch us in the hallway. Phew. Thank you.
Thanks.